Now that we have the coordinates, we can solve the problem by applying the conservation laws that we know. First, let's take a look at the conservation of angular momentum. We have an angular momentum connected with the orbit that is equal to the arm times the linear momentum. In this case, if you look at one dumbbell, you can consider, for example, that arm of the first mass is 0, so it doesn't take part in it. The arm of the second mass, m, is 2L, and you get in total for the arm 2L times the mv, and that's the angular momentum of one dumbbell. In reality we have 2, so before the collision the total angular momentum is 4Lmv, and afterwards the angular momentum due to the orbit is the same, but then with a u. We don't have only the angular momentum of orbit, but also of the spin after the collision. And angular momentum connected to spin, that's given by the moment of inertia times the angular velocity. Now the moment of inertia of any mass is the mass times the distance squared. In this case the mass is 2m, and the distance from the center is L. So this is the rotational momentum of a dumbbell, and this is the whole total angular momentum due to the spin of one dumbbell. So if you take both of them, this is 4ml squared omega. This can be reduced to a much simpler equation, and then we are left with this very simple equation, which have the relation between the speed before collision and after and rotation. But we have another conservation law, the one of kinetic energy. You all know it by heart, of course, the one connected with translation, 1/2 mv squared. In this case, if you work it out, you have 2 dumbbells, and then the mass of them is 2m, so then you get for the total kinetic energy before the collision this term. After the collision, the v is replaced by u, but in addition you have the term connected with rotational kinetic energy. You can write it out. It is 1/2 times the moment of inertia times the angular velocity squared, in which we fill in again the moment of inertia, and then we end up with this term, which again can be simplified a lot, and then we end up with this simple equation. Now we can look what happens if you combine the two equations. Here I've written them down again. You can find it out quite simply by yourself that the following two possibilities are solutions to this problem. The first one, the velocity hasn't changed and there is no rotation after the collision. And that's a strange solution, because that would imply that the two dumbbells would go straight through each other, and that cannot happen, of course. In the second solution, the velocity after the collision of the centers of mass is 0, and all the rotational energy has been translational energy has been transferred into rotation. And that's of course a possibility. Let's take a look what it looks like. We get the collision, we get rotation, but then we get a second collision. And in the second collision, you can have as a solution, of course, this equation. So in a way, if you look back, then you see that the translation in a way just continues, but then with flipped dumbbells. I really like this solution. It's a very simple solution, but I must say that in my daily life I see this very often. In my daily life I'm not a lecturer classical mechanics, I'm a physicist who is scattering polarized neutrons. Here you see a photograph of the setup. neutrons are being polarized here. Then you go through a whole set of magnets, and in each magnet the path of the neutron is just going straight ahead, but the spin of the neutrons is being flipped. So it's very similar to the problem that you just have solved. I hope you enjoyed it. See you in the next exercise.